Okay, Russ Jackson, we're diving into building a command line tool, a version of grep. Can you give us a quick overview of what grep does and why it's useful?
Sure, Matthew. grep, globally search a regular expression and print, find specific text patterns in files. It's a fundamental tool for anyone working with text data. Imagine you have a huge log file. grep lets you quickly find entries mentioning a particular error code, for example, saving a ton of time.
So, this project will be like a simplified version of grep?
Exactly. We'll learn a lot about Rust by creating something useful. Plus, we'll see how to handle command line arguments and interact with files and the terminal effectively.
Interesting. What core Rust concepts will we be using?
We'll use concepts like organizing code with modules, working with vectors and strings, handling errors gracefully, utilizing traits and lifetimes, and of course, testing our code. There's even a sneak peek at iterators and closures.
That sounds pretty comprehensive. What about error handling? How important is that in a command line tool?
Crucial. Command line tools often deal with unpredictable user input. Robust error handling prevents crashes and provides useful feedback to the user. Think of unexpected file paths or incorrect commands. Good error messages are key to usability.
Right, user experience is vital. So, we're essentially building a program that reads files, searches for specific strings, and outputs results.
Precisely. We'll also explore how to use environmental variables for configuration and how to direct output to the console or a file, separating error messages and successful results.
How about dealing with multiple files?
Good point. Our simplified grep might just look for a single file at first, but we might enhance it to handle multiple files, too.
That's clever. This project will tie together a lot of different components, like handling command line arguments and interacting with the file system, right?
Yeah, integrating different parts of the system is crucial. It will force us to understand interactions between modules, variables, functions, and the overall structure of a Rust program.
So, what are the implications for financial applications?
Think about log analysis. grep helps find crucial data points in transaction logs. It's a powerful tool for debugging financial systems, ensuring data accuracy.
I see. What about using traits and lifetimes in this case?
Traits allow us to define shared behaviors, and lifetimes help with memory safety. We might use traits to define common operations on different data types and lifetimes to ensure data access is safe and predictable, especially if the input data is coming from multiple sources.
This looks like a very practical project.
Exactly. We'll combine these skills in a project that's both educational and potentially useful. It's a practical way to apply our Rust knowledge.
Great, Russ Jackson. Thanks for laying the groundwork. This promises to be a solid example of how Rust excels in building robust and efficient tools.
Glad to share, Matthew. Let's delve into the specifics of the code soon.
Russ Jackson, welcome back to the show. Today we're diving into command line arguments in Rust. How do we get those values into our programs?
Hey, Matthew. Great question. To grab command line arguments, we use std, env, args.
Vol, std, info, aux, nested modules, huh?
Yep, a common Rust pattern. It's like a well-organized file system for functions. We use std, env, to bring in the whole environment module, making the code cleaner.
So, it gives us an iterator?
Exactly. An iterator is like a conveyor belt that produces values one at a time. In this case, each item on the belt is a command line argument as a string.
And what's this collect? Magic.
Collect takes that iterator and turns it into a collection like a vector that holds all those arguments. It's super handy.
So, it's turning a stream into a list.
Precisely. And we need to specify what type of collection. We want a vec. Without that type annotation, Rust might guess wrong.
So, let's say I run cargo run hello world. What would the program see?
The program would get a vector containing 3 strings, the program name, cargo run, hello, and world.
Interesting. Why the program name?
Because it's standard behavior in most programming languages. It lets the program know how it was launched, which can be helpful in various situations.
Great. But what if the argument has invalid Unicode?
Then std, env, args would panic. That's not good. So std, env, args under stress is safer. It handles those cases.
So args under stress returns OS string, which is platform dependent?
Yes. It can represent different types of strings depending on your OS. For simplicity, std, env, args is the more straightforward approach.
Is there a real-world financial application for this?
Certainly. Think about a program that processes financial data from the command line. The arguments could define the input file, output file, or filter criteria. Using collect lets you treat that data as a structured list.
Got it. So collect is a crucial tool for dealing with command line arguments in a more sophisticated way.
Precisely. It takes the stream of command line data and makes it ready for use in your program's financial calculations.
What about potential problems people might run into?
People might forget to include the right type annotation or forget the use statement. Also, some programs require specific argument types. So, always validate inputs.
Great points. It's important to understand these nuances, especially in financial apps. Thanks, Russ Jackson. Russ Jackson, welcome back to the show. We're diving deeper into command line arguments in Rust today. Let's talk about saving those argument values. How do we actually store them for later use?
Sure, Matthew. Crucially, we need to extract those values from the vector and put them into variables we can reference.
So, we're taking data from that vector and assigning it to specific variables. Can you explain how that's done?
Yeah, we use indexing. The args vector, remember, contains the program name plus all the command line inputs. So the first element, args0, is the program name. We want to get the second and third inputs, query and file name.
Got it. So, we're basically picking out the desired pieces of information from the input vector. What are the potential problems here?
Well, a crucial point is indexing. If we try to access args1 when there's only one argument, we get an error. This is often a cause of crashes in applications. This code needs robust error handling.
Excellent point. Error handling is critical. You mentioned handling cases with fewer arguments than expected. What's another way to consider this, practically speaking?
Consider a user interface. A robust program would check if enough arguments are provided, giving the user helpful instructions.
You're emphasizing the importance of validating the input. This is fundamental, right?
Precisely. We're taking a crucial step now, checking the validity of the user input. A financial application, for instance, could use command line arguments to make trades, so incorrect parameters could be disastrous.
So, to reiterate, we're indexing into the args vector to extract the values we want. What happens if there are fewer arguments than expected? How do we handle the potential error?
We should add checks to prevent the code from crashing. We'll need to account for potential errors.
Okay, this is really clarifying how critical error handling is. So, what happens if the user supplies the wrong data types?
We need to be careful about the data types. We're assuming the second argument is a query string and the third is a file name. If the user enters a number, the program will fail. So, validation is needed to make sure the inputs are in the expected format.
So, we're not just dealing with the number of arguments, but also the kind of argument.
Exactly. We need to validate that the input data is correct.
Right. To prevent crashes and ensure the program works as expected. Let's emphasize again that we're taking the elements from the vector and assigning them to variables, and the potential for error if those elements aren't there.
Correct. This is essential for building robust programs. We're moving from simple data input to processing.
Thanks for explaining this clearly, Russ Jackson. Now we're better equipped to consider more sophisticated data handling. Russ Jackson, welcome back to the show. Today we're diving into reading files in Rust. So, we've got this poem.txt file, right? How do we get its contents into our program?
Yeah, Matthew. We're leveraging the standard library. Basically, we need to use the FS module to interact with the file system.
Okay, so FS, like file system, makes sense. And how does that help us read the file?
Precisely. We use FS, read_string. It takes the file name as input and tries to read the entire file's contents into a string.
So, FS. Read_string is like a function that does the reading for us?
That's right. It returns a result. Think of result as a container. It might contain the string we want if the reading was successful, or it might contain an error message if something went wrong, like the file wasn't found.
So, it's not just a simple retrieval operation?
Exactly. It's safer. It handles the potential problem of the file not existing or being inaccessible.
And how do we deal with that potential error?
We use pattern matching, or the operator, which is a shortcut for pattern matching, to check the result. If it's an error, we handle it. If it's a string, we work with the file contents.
Right? You need to handle the possibility of errors. So, if the file doesn't exist, what happens?
The program would stop, and we'd see an error message. The fs, read_string function returns a special type, result, which lets us handle both success and failure, making our code robust. Think of it like a safety net for file operations.
So this robust design makes it easy to use with different types of files, like in finance, right?
Definitely. For example, we could read transaction logs or financial reports. In finance, reading data from files is crucial.
Speaking of finance, what if the file is really big? Could fs read_string handle that?
It might not be the best choice for extremely large files. It loads the entire file into memory at once, which could cause memory issues. There are other approaches for handling large files in Rust. You could process them in chunks, or read only the necessary parts. That's crucial in managing large datasets for reporting and risk assessments.
So, you're saying we should be mindful of how we're handling files and not just read them in memory?
Absolutely. The code in the example has a few limitations. It's good to consider memory management and error handling while working with files, especially in production environments or systems dealing with high volumes of financial data.
Russ Jackson, great insights. So we know how to read the file, but now the challenge is handling potential errors, like file not found or permission problems.
That's correct. We have to add error handling to ensure our program can recover gracefully from these issues and prevents our program from crashing.
So what are some other implications of this for other types of financial data processing?
For example, it's crucial for handling financial data because reading and processing large files correctly ensures the accuracy of reports and the avoidance of errors in calculation.
Very well said, Russ Jackson. Excellent discussion of the details of reading a file. Hey, Russ Jackson, let's talk about separating concerns in binary projects, especially in Rust. This separation idea seems pretty crucial, right?
Absolutely, Matthew. It's a common problem. One big function in your program can become a nightmare to debug and test.
So, how does this separation work exactly?
We move a lot of the program logic from the main function into a dedicated module, often librs.
Okay, can you give me a real-world example?
Imagine building a trading platform. You'd have logic for handling user orders, checking balances, calculating fees. Keeping all that in main.rs makes testing very hard.
How do we move that logic over?
Well, we move the core functionality to librs. Then, main.rs just orchestrates things. It parses command line arguments, configures the environment, and calls the functions in librs.
So main.rs becomes more of a manager.
Exactly. The smaller main.rs is easier to understand and test.
What about complicated command line parsing? How does it fit into this?
At first, parsing might be simple enough to stay in main.rs, but it can get complex. Move it to librs when it becomes a significant part of the logic.
What are the benefits of this approach?
Testability, mainly. We isolate the logic for testing, making it easier to see if components do what we expect. This also leads to better maintainability and readability.
What are the drawbacks?
Could potentially lead to increased initial complexity with more files. But that's often worth it in the long run.
Is there a way to measure the impact in a real-world financial context?
Absolutely. For a trading platform, reduced debugging time in testing translates to faster time to market and fewer costly errors in production, which directly relates to profits.
You're saying better testing equals better performance.
Potentially, yes. Faster turnaround equals more trades processed and potentially greater profits.
So, even if it takes a bit more setup initially, It seems like separating concerns in main.rs and lib.rs is the way to go for larger projects.
Absolutely. The maintainability and testability you gain often outweigh the initial effort. It's really about building for the future.
Great. So, basically, keep main lean and focused on orchestrating, moving the rest to a library for easier testing and maintainability.
Exactly, Matthew. This is a great technique not just for Rust, but good practice across many programming languages.
Russ Jackson, thanks for the insights. Really valuable stuff.
You're welcome, Matthew.
Okay, Russ Jackson, let's talk constructors. We're moving from a plain function to a constructor. Can you unpack why that's a good change?
Yeah, Matthew. So, before, our parse_config function was just doing its thing. Now, we're making it a method of the config struct. This makes our code way more organized and readable.
So, it's about organization, you're saying? How does that make our code cleaner?
Precisely. We're tying the parsing logic directly to the config object. It's now clear that parse_config is fundamentally about creating config instances.
And how does this tie into the query and file name relationship?
Great question. By making parse_config into the new method, we're highlighting that the query and file name values need to be associated with a config. The config struct directly owns these values, which is much better than having them floating around in a function.
How is this beneficial, like, in the real world?
Well, imagine a finance app. You need to fetch data from different files based on user queries. This approach ensures your data is always tightly controlled. You wouldn't want queries and file names scattered around. They must be together.
Right. And this is more like object-oriented programming, OOP. How's that helpful?
This is idiomatic Rust, using its OOP-style features to improve code clarity and reduce potential errors. It's easier to understand and maintain the relationship between the data.
Okay, so the new method inside the config implementation handles the values, query, and file name. So what's the deal with the and_args bit?
The and_args part means the function is borrowing the args slice. It's not taking ownership. This is super important for efficiency.
How's that different, like in practice?
If we didn't borrow, we'd copy the entire args slice, which could be large and expensive. Borrowing avoids that overhead.
Okay, I'm seeing the pattern. By using the new method, the config now owns the query and file name information, right?
Exactly. It's clear how these pieces of data are related and belong together, leading to more robust code.
What about error handling? What if args doesn't have the expected values?
Excellent point. We'd want to add checks to make sure the array has at least 2 elements. We could return a custom error type if the input is invalid.
Okay, good example. So, this approach is about more than just syntax. It's about clear code design?
Absolutely. It's about modularity, organization, and clarity. The new method is an essential way to create objects and structure your logic.
Okay, I think I'm starting to get it. Let's talk about
Interrupting. Using this pattern for other kinds of data structures too?
excellent. This approach clearly scales. Let's move on. Russ Jackson, welcome back. We're diving deeper into error handling in Rust today. This new result approach. Interesting stuff.
Thanks, Matthew. Yeah, result is a powerful tool for handling potential errors gracefully. Instead of panic, we're returning a result value.
So, panic abruptly stops execution, right? What's the problem with that?
Exactly. Panic is great for debugging, but it's not ideal for user-facing applications. It dumps a lot of unnecessary technical details. Imagine a user seeing a cryptic message about a thread or a backtrace. It's not user-friendly.
So, result provides a more controlled way to handle these situations. Explain that a little further, please.
Result wraps up the possible outcome. Either a config instance, success, or an error message like a string literal, failure.
Show me an example. How does the function look?
Well, the config, new function now takes a vector of strings, args. If there aren't enough arguments, it returns error, not enough arguments. Otherwise, it constructs a config struct and wraps the result in OK, config query, file name.
So, this OK and error, They're the key here.
Precisely. They let the calling function differentiate between a successful creation of the config and a failure. Think of it like a traffic light. OK means clear, err means stop.
What does the static mean in result?
And static str means the error message is valid for the entire program's lifetime. It's a string literal, so it's part of the code itself and will never disappear.
I see. This approach of propagating the result up the call stack is crucial, isn't it?
Absolutely. The function main is now responsible for handling the result returned from config, new. It can gracefully respond to errors, such as displaying user-friendly messages.
So, a potential error doesn't just abruptly halt the program.
Correct. The program can now handle the errors and choose appropriate responses, like displaying an error message to the user and exiting cleanly.
Makes sense. Real-world application. A financial app. If a user forgets to enter some required information.
Yes, exactly. Instead of crashing, it returns an error, like missing required data. The app can handle this gracefully by showing a user-friendly error message and ask for the missing info. Think about potential network errors.
Great. This error handling, it sounds far superior to just panic. Very practical for the market.
Definitely. The result type fosters robust and user-friendly applications. It's a fundamental aspect of writing reliable Rust code.
Excellent point. Russ Jackson, thank you for your insights. This really helps to understand the power of error handling in Rust.
Thanks for having me.
Russ Jackson, welcome back to the show. Today, we're digging into error handling in Rust. You've been talking about config. New. Can you walk us through how to gracefully handle potential errors when creating a config object?
Sure, Matthew. We want to avoid crashing the program when config new encounters a problem like missing arguments, right?
Exactly. How do we do that without the whole app going down?
We use unwrap__else. It's a powerful tool for handling result types. Imagine config new returns either a config object or an error message.
So, like a promise, right?
Exactly. Unwrap__else lets us do something different if we get an error, instead of panicking.
Can you show us how that works?
In the code, we use a closure to handle the error. We print a friendly message in use process, exit1, to stop the program and tell the operating system there's been a problem. This is important for signaling that something went wrong back to the program that called minigrep.
Why process? Exit1?
It's a standard convention. A non-zero exit status tells the calling program that minigrep failed.
So, if we get an error, the program prints a message, quits, and indicates a failure to the caller? Makes sense. But how does it get the error message?
Unwrap__else receives the error as an argument. This is a crucial part of the result concept in Rust. It gives us a way to handle the error case. The closure gets the error itself, not just a Boolean telling us there is an error. It's the error's content, like not enough arguments, that the closure uses.
So this is better than panic, because
it's more controlled. Panic dumps information and then crashes, which can be useful during development, but in a production environment, it can be more complicated to deal with, and we would not want to display the stack trace to the users.
this feels like a more responsible way to exit a program if something goes wrong.
Definitely. We're providing a better user experience and a cleaner way for other programs to understand what went wrong. Imagine using this pattern in a program that processes financial transactions.
You mean like an API that calculates risk? How might a bad input affect that API?
If the input data is not in the expected format or missing required elements, our config new function would return an error. Instead of crashing, this structured error handling would let the API report the error to the user, preventing a cascade of unexpected failures and potential financial issues.
Great point. Now imagine something that could go wrong in this financial risk program, but doesn't need to completely stop the program. How do we handle that?
Well, we might want to log the error and try to continue. We could return an error value containing the error details and let the caller determine the appropriate action.
This sounds like a crucial pattern for robust financial applications. Very informative, Russ Jackson.
Thanks, Matthew. It's a key aspect of building reliable and user-friendly software.
All right, Rust, so we're diving into the guts of this program now. You've extracted the run function. What exactly does that do?
Yeah, so this run function, it's like taking over the core logic. Think of it as the heart of the program. It's doing everything from getting the file contents to displaying the data.
Okay, so what are the inputs and outputs of this run function?
The input, as you see in the code snippet, is the config structure, holding all our configuration settings. The output is, just the printing of the file content to the console.
Gotcha. What about error handling? Is it taking care of that as well?
Not yet. We're just, taking the config as is and hoping it's valid, and that the file exists. We're not catching any potential file read issues. That's a next step, right?
Right. So it's a crucial first step. We're extracting logic cleanly, then adding in error handling and validation.
Absolutely. We're separating concerns, keeping the configuration setup and error handling apart from the core processing in main. This is good practice. It makes it much easier to test the run function in isolation.
Makes sense. So this run function in our program logic, how does it use the config structure?
Well, the function gets the file name from the config object. It then uses that to open and read the file. It's a critical part of the process, grabbing that file name to find the data.
Okay, so you're reading the file. What does it mean in practice? Are we talking about reading a CSV file or a JSON file or what?
That's open for design. This is just a template. It could be any kind of file as long as our config object holds the information needed.
So, there's potential for this function to be very versatile.
Yes. We're building flexibility into the code.
So, you're saying this run function could process a lot of different files. It's not limited to just one kind?
Precisely. The core processing is isolated from the file type.
That's a pretty important design choice, right? Modularity and flexibility.
Absolutely. It's all about keeping our code organized and reusable.
And, why this approach? Why not just leave everything in the main function? What's the benefit?
This separation is crucial for maintainability. When the project grows, keeping things tidy makes it simpler to maintain and add new features. It's like building with Lego blocks. Each block has a specific function. You can easily combine them in different ways.
So, in a large project, this makes sense. But what about a small project? Is it worth the effort?
It's still good practice. Even for small projects, the habit of separating logic promotes cleaner, more readable code, which simplifies debugging and makes future modifications smoother.
And, how about testing? This modular design simplifies testing?
Absolutely. You can test each component in isolation. Testing becomes much easier because you can isolate that run function, making your program less brittle as well.
So, a much easier and quicker way to test various aspects of this program.
Exactly. You're isolating the parts that might fail and test those parts individually.
That makes a lot of sense. So, we've gained modularity and testability, but what potential pitfalls might we encounter in general?
Potential issues include making sure the functions communicate properly, or even unintended side effects from one part impacting the others. But this separation design usually avoids these problems. The separation makes code much more predictable.
Great insights. This refactoring looks really helpful. Welcome back to the show, Russ Jackson. Today, we're diving deep into error handling in Rust. You've got a great example here.
Thanks, Matthew. Error handling is crucial, especially in financial applications. Imagine you're processing a transaction. A little error can lead to a huge problem.
Absolutely. Let's look at this run function. Why do we change it to return result?
Previously, if there was a problem reading a file, our program would just crash. Using result allows us to gracefully handle the error. It's like a safety net.
So, result, that's a bit complex. Break it down for us.
Result is a general way to deal with possible errors. Is the type for when everything works as expected, nothing returned. Box is a powerful feature. It means we can handle any type of error the program encounters without needing to know in advance. It's really flexible.
So, box is like a general error container?
Precisely. Imagine different types of errors: file not found, permission denied, network issues. Box can capture them all.
And what about the operator? That's a new one.
It's a shortcut for handling errors. Instead of explicitly checking for errors, The operator will propagate the error to the calling function. It's extremely elegant.
What if, instead of a file read error, we had an invalid input error in a financial transaction?
Then, that specific error type would be part of box. The calling function would handle it appropriately.
Okay, so we have error handling, but what happens if we don't deal with it?
The compiler gives you a warning, because the result value is potentially an error and needs to be handled.
So, the compiler's helping us catch possible errors.
Exactly. It encourages robust error handling. If we had a warning in a financial app, we could miss a critical error and see unintended negative impacts.
So, we've made our code more robust by using result?
Absolutely. This also improves maintainability. You can add error handling for new operations without changing a lot of existing code. Think of it as modularity for errors.
A huge improvement over crashing, and it gives you valuable warnings.
Indeed. This approach is common in Rust and helps ensure that errors aren't silently ignored.
You've explained all this incredibly well.
Glad to help. Error handling is key to writing reliable programs. It's important, especially in high-risk systems like financial applications.
Russ Jackson, thanks for joining us today. We're diving into test-driven development, TDD, for minigrep. Can you explain the TDD process?
Sure, Matthew. TDD is a way to build software. We write a test first to specify exactly what a piece of code should do. Then, we write the minimum code needed to make that test pass. Finally, we refactor that code to be more efficient and maintainable.
So, why write the test before the code? Seems counterintuitive.
It's about clarity. Knowing what the code needs to do beforehand helps us design it better, reducing bugs and improving maintainability down the road. Think of it as setting the destination before picking the route.
Okay, but how does this translate to something like minigrep?
We'll use TDD to build the search functionality. We'll start by writing a test for the search function that expects it to find a specific line in a text. This ensures we clearly understand the expected input and output.
And then we write the function, right?
Precisely. We'll write the bare minimum code to satisfy the test, then refactor it for elegance. This ensures the code is working exactly as we want, and with minimal code.
Sounds like a good approach. What if a file doesn't have the line we're searching for?
That's a critical aspect. Our test will handle those edge cases, ensuring our search function gives the correct response when the line isn't found. That way, the program doesn't crash or return incorrect results.
Excellent. So we're setting up this search function within the context of the config object?
That's correct. Testing the config object now that we have our search function encapsulated within is a smart way to isolate and thoroughly test its internal logic.
How does that help with financial applications?
Imagine a program verifying customer transactions. TDD would help guarantee that the verification logic is correct and robust for every possible input, including invalid data. Robustness is key to avoiding costly errors in finance.
So, for minigrep, we're focusing on the core logic of search within the config object?
Yes. We'll establish the expected behavior first, and then write the minimum code needed to pass each test. Then we'll focus on clarity and code structure for efficiency.
Sounds like the right approach for minigrep. Can we see an example?
Not yet, but I can show you how we'll start writing those tests, focusing on expected failure first.
Great. Let's move into the concrete implementation.
Right. We'll build the tests, then the code, ensuring high test coverage. It's about creating reliable software through thorough testing.
Thanks, Russ Jackson. This is helpful. All right, Russ Jackson, let's dive into this failing test. We've got a search function, but it's currently returning an empty vector. Why does this test fail?
Well, the test is expecting a vector containing one string, safe, fast, productive, when the function returns nothing. It's a simple mismatch.
Okay, so it's just a matter of getting the function to return the correct data. But what about this lifetime annotation? Hey, it seems a bit abstract.
Yeah, lifetimes are a bit of a head-scratcher at first. Think of it like borrowing. We're borrowing parts of the content string, so we need to tell Rust how long those borrowed parts will live. Without it, Rust can't guarantee those slices will still be valid when we use them later.
So, it's ensuring the borrowed parts of the text are available while we're using them. How does that connect to our function returning a vector of string slices?
Exactly. The function search takes a query string and a string to search within. Crucially, it returns a vector of string slices from that input string. The lifetime annotation ensures those slices are valid as long as the input string itself remains valid.
So, if the input string is gone, the slices are gone too? That's critical. Any real-world applications for this?
Definitely. Imagine a financial data analysis program. You might be searching a log file for specific error messages. If the log file is deleted or overwritten before the analysis is complete, the results would be meaningless or worse, corrupted. The lifetime annotation guarantees that won't happen.
Gotcha. So, what if we just had the function return the full string instead of slices? Would we need the lifetime annotation then?
Not exactly. If we return the entire string, there's no risk of the original data being gone. The lifetime only comes into play when we're dealing with parts of that data.
And what if the query was the thing that needs to have a longer lifetime?
That's where the code would have to change the order of the parameters in the return value and use the query lifetime in the search function. This would be different from the example we have here.
Okay, so the lifetime isn't just some obscure programming concept. It's essential for maintaining data integrity.
Precisely. The lifetime annotation helps prevent a common mistake in programming, where a borrowed part of memory may be invalidated before it's used. This isn't specific to finance, but financial applications often deal with complex data structures.
Thanks for breaking it down. So, how do we get our test to pass? We need the function to return the correct data?
Yes, we need to modify the function to return lines containing the query. That would involve checking each line of the input text.
Right. Just to recap, search needs to scan the input string for the query and return the matching parts.
Right. With the correct search logic added, the function will return the expected vector, passing the test.
Perfect. This is a crucial concept for writing robust, reliable code, especially in applications with potentially large or complex datasets. Thanks, Russ Jackson. Russ, let's talk about fixing this failing test. We're always returning an empty vector, right?
Yeah, we need to actually search the input.
So, step one is iterating through each line. Can you explain that in more detail?
Sure. Think of it like reading a document, one line at a time. Like, if you're trying to find all the mentions of a specific stock ticker, you need to go through each line of the trading data to see if it's there, right?
Makes sense. And how do we compare the line to our search query?
That's the second step. We use a comparison method, checking if the line contains the query string. Like searching for GOOG in a news article, we look for that exact string.
So, if a line matches, we add it to our result list?
Exactly. That's step 3, building up a list of matching lines.
And if it doesn't match, what happens?
Nothing. We move on to the next line. It's a simple process of inclusion, basically.
That's clear. So, what's the last step?
Return the list of results.
So, we're building a search functionality, right?
Precisely. This is a fundamental search pattern. You can use this to find text in documents, financial records.
This is super helpful for financial applications. Say we wanted to find all entries for Apple in a year's worth of trades.
Totally. This code snippet directly enables that.
But could this encounter edge cases or problems?
Well, if the input data is really huge, performance might become a concern. Large datasets could take a long time to scan.
Good point. How do we optimize that for really massive datasets?
You could use techniques like indexing or partitioning the data, so we search smaller blocks.
What if the search query is something like APL followed by a number? Would this code handle variations of this?
No. This code is very literal, looking for an exact match.
That's important to note.
For more complex searches, we'd need different strategies. Regular expressions, for instance, could allow us to find patterns instead of just exact matches.
Okay, so regular expressions would be the next step for expanding the search capabilities.
Absolutely. You'd need to learn to use regex, but it's a useful tool in situations where exact matches aren't enough.
Thanks, Rust. That was extremely helpful.
Anytime.
So, step by step, we've built a simple search function. It's crucial for financial data analysis. Russ Jackson, welcome back to the show. Today, we're diving into Rust's powerful line-by-line string processing.
Thanks, Matthew. Excited to talk about it. So, we're looking at how to iterate through strings line by line, right?
Exactly. This lines method looks interesting. Can you give us a high-level overview?
Sure. It's a built-in iterator in Rust. Imagine you have a big text file, or a string that contains multiple lines. You can use dot lines to get each line as a separate string.
So, it's like a loop, but it's tailored for strings with new lines?
Precisely. It handles all the messy details of finding those new line characters, making it super convenient. It's very useful for parsing log files or configuration files, for example. Think of a CSV file. You need to extract each row or line, right?
Right, this seems straightforward. How will we actually use it practically?
Let's say you have a string with multiple lines, like a poem or a simple code. You call the lines method on that string, and it returns an iterator that yields each line one by one.
So, you're saying it iterates over the string, stopping at every new line?
Yes. Rust manages the underlying data, so you don't have to worry about how it locates the new lines.
Great. So, it's essentially extracting those new line-separated portions.
Exactly. It's elegant and highly performant.
What are some use cases beyond log files or CSV?
Anything involving structured text. Imagine financial data in a fixed-width format. You can extract the columns easily, line by line.
But are there any caveats? What are potential issues or use cases where this approach might not work best?
If your string doesn't have proper line breaks, you might not get the desired effect. Or if you have an enormously large string that uses new line characters very sparsely, you might not want to hold the whole thing in memory at once.
So, memory efficiency could be a consideration?
Absolutely. Lines provides an iterator, which is very memory efficient. It processes one line at a time, rather than loading the entire string into memory.
That sounds much better for large files. So, in summary, the lines method is a fantastic tool for parsing structured text?
Yeah, absolutely. It allows you to work with and process that structure very elegantly, a must-know for any Rust programmer.
Great insights, Russ Jackson. This was super helpful. Thanks for clarifying that.
You're welcome, Matthew. Glad to help.
All right, Russ, let's talk about this line-by-line search. So, we're checking if a line contains a specific query string, right?
Yeah, exactly. We're using the contains method. It's a super handy built-in way to see if one string is part of another.
So, how does contains work? Like, what's going on behind the scenes?
It's really straightforward. It basically compares every character in the lined string to the characters in the query string, one by one. If it finds all the characters of query in line in the same order, it returns true. Otherwise, false.
So, if I search for Rust in a line containing the best language is Rust, it would return true?
Absolutely.
Cool. And what are the potential use cases for this? Like in a financial context, how could we leverage this?
You could easily filter transactions, identify relevant keywords in financial reports, or extract specific details from logs. Imagine searching for entries with stock XYZ or dividend payment. Pretty useful, huh?
Right? So, this contains method is really efficient, is it?
Well, generally it's pretty efficient, but there are potential performance considerations depending on the size of the query string and the number of lines to process.
Are there situations where it might be less efficient?
Absolutely. If your query is extremely long or if you need to search through massive datasets, you might see a performance hit. For huge datasets, a more specialized algorithm might be faster.
Got it. So, are there any common mistakes or pitfalls people might encounter when working with the contains method?
One potential problem is, people often overlook cases where the query string might match a substring of a different word in the file. That's something to keep in mind for accurate results.
So, a word of caution when using it with huge datasets. Good point.
Exactly.
What other methods could be used if you need a more advanced search than contains does?
You could use regular expressions for more complex searches. You could also use specialized libraries for even more advanced text processing tasks. But for a straightforward, is the substring there check, contains is fantastic.
So contains is pretty practical for a lot of situations. Thanks for explaining that.
Anytime.
Let's move on now to other search options. Russ Jackson, welcome back to the show. We're diving deeper into Rust today. So we've got this search function, and it's working. But are there better ways to do it?
Absolutely, Matthew. The current search function works, but it could be more efficient and elegant. We're storing all lines into a vector, but we really only care about the ones that match.
Right. So, more efficient in what ways? And what's elegant about it?
We're creating a whole vector, then returning it when we really just want those results. It's like ordering a whole pizza when you only want a slice.
A great analogy. So, what's the cleaner, more efficient approach?
Using iterators to filter matching lines. We could create an iterator to examine every line and filter for the ones containing the query string. This is more resource-friendly, especially with gigantic files.
This iterative filtering, that sounds interesting. Can you give us an example, perhaps with some financial data?
Sure. Let's imagine we have a log of stock trades. We want to find all trades where a specific ticker is mentioned. Instead of reading every line and then selecting the results, we only read the relevant lines.
So, we're selectively choosing and ignoring data. That's smart.
Exactly. It's like searching a massive database for relevant records, but only examining the necessary parts of the dataset. Much faster.
So, no more unnecessary loading and processing. Just focused retrieval.
Precisely. And this approach is not limited to finding stock trades. Imagine finding all lines in a large accounting report that mention a specific expense. We can do it more efficiently.
Cool. So, what are the key takeaways?
Iterators in Rust allow more concise and efficient filtering. It focuses on what you need rather than processing everything.
What about situations where there aren't any matches?
Well, with iterators, that would be handled elegantly too. The iterator will simply yield no matches, without creating an unnecessary empty vector. It would handle empty results very nicely.
Got it. This iterator's approach feels quite optimized, especially for large data sets. What if, for example, something went wrong? Maybe the file doesn't exist?
Error handling is crucial, always. We'd need to handle cases where the file path is invalid or the file doesn't exist, potentially returning an empty vector in those circumstances or throwing an error, depending on the application requirements.
Great points. So, using iterators can dramatically improve efficiency, particularly when dealing with large data sets, or when you only want specific information.
Exactly. It's a fundamental principle in efficient programming, which becomes increasingly important when working with large datasets in financial modeling or other data-heavy applications.
Thanks for shedding light on this, Russ Jackson.
My pleasure.
Russ Jackson, welcome back. We're diving deeper into mini-grep today. So, we've got this run function now. Can you walk us through how it uses the search function?
Sure thing, Matthew. The run function takes the user's search query and the file contents as input. It then calls the search function, passing both of those along.
And what does search do? Does it return the entire file contents?
No, it returns just the lines that match the search query. That's crucial. It's not just a basic search and replace, right?
Right. And then the run function loops through those matching lines and prints them one by one. So, the file's entire contents aren't printed to the console, only the selected ones?
Exactly. It's super efficient. Imagine searching a gigantic log file for a specific error message. You don't want to read the whole file. You only need the lines that are relevant to your search.
So, it's quite a different approach from, say, a simple file reading program.
Absolutely. This is a powerful way to use the power of Rust's design elements like the for loop and efficient file interaction techniques. You know, it demonstrates a focus on optimizing the user's experience.
Interesting. So, in this run function example, you're making use of a very targeted search over the file rather than a full read. That's a significant improvement over simply printing the whole file.
Exactly. This example highlights the importance of carefully tailoring code to achieve maximum efficiency and efficacy.
Makes sense. And with those examples in the code documentation, you can see how different search patterns produce different outputs, and that's critical.
Absolutely. It shows how the user can control the output based on what they search for.
Great explanation, Russ Jackson. Let's talk about the practical implications for, say, financial applications. Could this mini grep-like utility be used to process large datasets?
Definitely. You could use it for filtering transaction logs to identify unusual activity. Think of it as a powerful tool for financial risk assessment.
So, Run is taking that filter input based on a query.
Exactly.
What if a user enters something like invalid transaction?
It would search the transactions and print only those lines that contain that exact phrase.
So, Run prints only matching lines from the file, not the whole file?
That is correct.
What happens if the search query isn't in the file?
It just doesn't print anything. It's an efficient way to deal with non-matching cases.
Let's say there's a bug where the input file isn't correctly formatted. Would that affect the output?
Yes, the output would reflect the errors in the input file. For example, an unexpected character, a missing line, or incorrect data could lead to unexpected output.
Excellent. So, to summarize, we've learned how the run function calls search and then processes the matching lines efficiently. This run function allows you to search through data quickly and only prints what you need without unnecessary overhead.
That's right. We see the value of targeted searches in processing large datasets and the practical applicability for handling financial logs and risk management.
That's really insightful. Thanks, Russ Jackson. Russ Jackson, welcome back to the show. Today we're diving into environment variables. How can we use them in a program like MiniGrep?
Hey Matthew, thanks for having me. Environment variables are a powerful way to customize program behavior without changing the code itself. It's like giving a program a secret note.
So, you're saying we can make MiniGrep case-insensitive just by setting a variable? How does that work exactly?
Precisely. We can set an environment variable that tells MiniGrep to ignore case during the search. It's a sort of one-time instruction for the session.
That sounds useful. But why not just make it a command line option? Wouldn't that be simpler?
It's not necessarily simpler. It's more flexible. Imagine a user who runs MiniGrep multiple times in a terminal session. You save them from repeating the command. They set the variable once and it applies to all their searches. It's really a better option for frequent users.
Okay, so practically, how would this improve things, say, in a financial application?
Well, imagine you're analyzing huge datasets of stock tickers. You could set the case-insensitive flag for environment variable and search through all your historical data without having to type it every time. It speeds up repetitive tasks and reduces errors.
Interesting. Could you provide a counterexample where this approach might not be ideal?
Sure, if you're collaborating with multiple people in the same environment, some people might have this flag set to case-insensitive and some not. Then you could get conflicting results. Also, for infrequent users, it is unnecessary.
So, a trade-off between user convenience and consistency. A key consideration.
Exactly. You need to consider the context. For frequent users, it enhances their workflow. For others, it might be redundant.
What are some potential pitfalls or troubleshooting scenarios for this environment variable approach?
One is that misspellings or typos in environment variable names could cause programs to misinterpret or not function as expected. The other is that some users might accidentally set the variable in a way that interferes with other programs.
So, to recap, setting an environment variable for case-insensitive search in MiniGrep offers a powerful level of flexibility to users of programs like that. But it's crucial to understand when this approach makes the most sense in terms of user groups and workflow. Correct?
Absolutely, Matthew. Understanding the trade-offs between flexibility and consistency is crucial.
Thanks, Russ Jackson, for this insightful discussion.
My pleasure, Matthew.
Hey, Russ Jackson, let's talk about writing failing tests for this case-insensitive search function. What's the first step?
Okay, Matthew. First, we need a test that expects to fail. We're setting the stage for our new function, search_insensitive, by creating a test that will, well, fail.
So, a failing test. Why is that important?
Because it's the cornerstone of TDD, test-driven development. We write the test before we write the code. It forces us to clearly define the desired behavior, the input, and the expected output of our function.
Makes sense. How do we structure this failing test, then?
We'll use a testing framework like in listing 12 to 16, for example, which helps us define the inputs and expected outputs for our function. We'll write a function that calls search_case_insensitive, providing data to it, then ensuring the result matches what we want. Crucially, since search_case_insensitive doesn't exist yet, the test will fail.
Right, a test that will inevitably fail because the function is missing. Is there a reason why we want to write the failing test first?
Absolutely. It lets you focus on the problem before jumping into the solution. You clearly define what you're building, avoiding hidden assumptions and making it obvious when the expected outcome isn't delivered.
Sounds like a good design practice. What would this failing test look like? What does the error look like?
The test will basically call a function and expect a certain outcome, but the function hasn't been built yet, so it'll produce an error. A compilation error specifically.
And how does this relate to financial applications, for instance? Are there cases where failing tests could be beneficial?
Absolutely. Imagine you're building a trading algorithm that calculates profits. A failing test will highlight if the algorithm incorrectly handles certain edge cases, like a market crash or a sudden order surge, before it goes live.
Great points, Rust. It makes the testing process easier to follow.
Exactly. Failing tests act as a safety net, helping you identify and fix flaws early in the development cycle, saving time and money down the road.
So, you're saying that failing tests are really the first step towards reliable software and a better approach to managing complex financial applications?
Precisely. You design your system and then test if the design works and if the components are behaving as expected.
Okay. Thanks for your time, Rust.